Welcome to a lesson on finding the area of regular polygons. An apothem is a segment that is drawn from the center of a regular polygon to a side that is perpendicular. It's very important to recognize that this is only used in regular polygons. And by regular we mean that all the sides are congruent and all the angles are congruent. Perimeter is the sum of all the sides of a polygon. In this first set of examples, we're simply going to draw the apothem on each figure. A three-sided polygon is a triangle. We would draw the apothem straight to the midpoint of a side, and it would be perpendicular. In a square, we would also draw it to a side, perpendicular. Same with a pentagon. Hexagons with 6 sides. Heptagons have 7 sides, and an octagon has 8. Typically, when you see an example of a polygon containing an apothem, it will be drawn to only one side. But I could actually draw it to all the sides, and all of the segments that are apothems would be congruent. So I could actually draw all 5 of these in if I needed to. Each apothem always creates a 90-degree angle with the side that it intersects, and all the apothems would be congruent. In order to find the area of a regular polygon, we need to know both the apothem and the perimeter. The formula for the area of a polygon is area equals 1/2 times the perimeter times the area. In this formula, we use a capital A to designate area, a lowercase a to designate apothem, and a capital P for perimeter. We're now going to do a few examples in which we'll use this formula. This first example, we're looking at a nonagon. A nonagon has 9 sides. It's important to read the question carefully and note that this is in fact a regular polygon. If it were not regular, I could not use this formula. The perimeter of a polygon is equal to the number of sides times the length of each side. Because I have a nonagon, the number of sides is going to be 9, and according to the question, it says that each side is 4 units. So 9 times 4 means that I would have an area of 36. The other piece of information I need for this formula is the apothem, and they've told me here that A is 7. So I'm simply going to plug in the information I have. 1/2, I'll substitute 36 for the perimeter, and I'll substitute 7 for the apothem. When I simplify, I will find that the area of this nonagon is 126 units. Because I'm finding area, my units would be squared. We frequently compare the area of a circle with the area of a polygon. So just as a reminder, the area of a circle is pi times the radius squared. So area equals pi r squared, in which r stands for radius. In the selected problems below, we need to find the area of the shaded regions, and it says to assume that the polygons are regular. So in this first example, I have a circle. Contained within the circle is a square. I know it to be a square because it's regular. Therefore, all the sides are the same. In order to find the yellow shaded area, I'm going to find the area of the circle and subtract the area of the square. So the area of a circle is pi r squared, and in this case, my radius right here is 9. It's important to notice that the radius goes from the center all the way to the edge of the circle. That's the radius. So my area will equal pi times 9 squared, and if I simplify, that comes out to 254. In order to find the square, I have the apothem, so this is actually A. You can tell the difference between the apothem and a radius because a radius has an endpoint on the circle, whereas the apothem has an endpoint on the polygon. Because the apothem is 4, if I were to extend this line all the way across, I would find that the side length of this square is 8. Keep in mind the area of a square is the side squared. So this area would equal 8 squared, which is 64. So in order to find the area that's shaded, I would take the area of my circle, 254, subtract the area of the square, 64, and I would find that the yellow shaded area is 190 units squared. Keep in mind that these drawings are not to scale. Clearly the square looks much larger than the shaded yellow area. In my next example, I am finding the area that is present in between a circle and a polygon that is inscribed inside the circle. In this particular case, I have a radius of 11. Notice that this segment goes all the way to the edge of the circle, so that's my radius. So the area of my circle will be pi times 100 or 11 squared, which will be 121 pi, which equals 380 approximately. To find the area of my polygon, I first need to find the perimeter. So I need to know how many sides are in my shape. And if I count the sides, I will find that actually I have a decagon. And in this decagon, I have 10 sides. So the perimeter will equal 6, because that's the length of each side. Notice here, this is the side length of the polygon, times 10 sides, which is 60. I'll plug P into the formula for perimeter, and A over here is 10 inches, that's the apothem, which I will also substitute into the formula. So I'm going to have area equal 1/2 the perimeter of 60 times the apothem of 10. And again, I know that this is the apothem because the end point is on the polygon and not the circle. So area will equal 1/2 times 60 times 10, which will equal 300. So in order to find the overall area, which is shaded, I'm going to have the circle, which is 380, minus the polygon, which is 300, which will equal 80 inches squared. That would be the area of this yellow shaded area. Our next shape is a bit more of a challenge. I'm actually looking for the space that is contained here in between the triangle and its inscribed circle. So I'm looking for all of this shaded here. Because these are regular polygons, I know that this particular triangle is an equilateral. That means I know that each angle will be 60 degrees. In order to find the area of a triangle, I need to use 1/2 the base times the height. The height, in this problem, we're going to change it to 5. So the radius here is 2 and the height is 5. So I have the height of my triangle as 5, but I don't yet know the base. In order to get the base, I need this whole length here. Because this is a 60-degree angle, if I were to extend this line, I would have a height of 5. This would create a 30, 60, 90 right triangle. Therefore, the base of half of this base here, would actually be the long side of 5 divided by the square root of 3. That's the property of a special right triangle with 30, 60, and 90 degree angles. So in doing that, I would find 5 over the square root of 3 is actually equal to 2.88, but I want the base of the entire triangle. So I'm going to double that number, and I'm going to find that this large base all the way across is actually 5.77. So this is the base of the equilateral triangle. So, with that in mind, the area of my triangle will be 1/2 times 5.77 for the base times a height of 5. When simplified, that comes out to 14.43, and that would be meters squared. So there's the area of my triangle. The area of a circle, again, remember, would be area equals pi r squared. So I'm going to plug in area equals pi. My radius here is 2, so I get 2 squared, or 4 pi, which will equal 12.56. So this is the area of the triangle. This is the area of the circle. So in order to find the difference, I'm going to do area of the triangle, which is 14.43, subtract the area of the circle, which is 12.56, and get a total area of 1.87, and that would be meters squared. Thank you for following this lesson.
Oops!